Let us understand how to generate sine wave signal using digital to analog converter, that is DAC. Now to write a program for a sine wave generation, we cannot use formula sine theta in program, in assembly language program. For that, now we have to compute values, magnitude values for different theta, that is from 0 degree to 360 degree manually, and these magnitude values will be stored in lookup table. In program, we'll read values of magnitude from lookup table and we'll give it to DAC. So DAC will convert these magnitude values into analog and then we'll get a sine wave output. Now we know that the values of sine function varies from -1 to +1 for theta from 0 to 360 degree. Now to increase these values, we'll multiply this sine theta by 5. So we'll get the integer values, and if we observe this sine wave signal, half of the magnitudes are having values negative, but we want all these values of magnitude positive. So we'll shift this sinusoidal signal above a 0 degree. So for that we'll add here 5 in this formula. So our final formula to compute the magnitude of sinusoidal signal will be 5 plus and bracket 5 into sine theta. We'll compute these values from 0 to 360 and then we can prepare a lookup table. Now this is the lookup table. So for different values of theta from 0 to 360 degree, I have considered here difference of 20 degrees. To get a precise sine wave, we can reduce this difference. That means you can take a difference of 10 degrees, you can take difference of 5 degrees. So in that case, the number of rows will increase. So this theta in degrees, I have first converted into radians. Then we have computed here sine of this theta value, and then as per the formula I have computed values 5 plus 5 into sine of theta. Using Excel we can compute these values also. Now we need this final column values to generate a sine wave using DAC and microcontroller. So for theta is equal to 0, our magnitude value is 5. For 20 degrees our magnitude value is 7, and here for 340 magnitude value is 3. So this lookup table will use to write a program to generate a sinusoidal signal. So DAC interfacing diagram we are using for all program is again shown here. You can watch a video of DAC introduction and square wave generation using DAC also. So here we are using port P1 of 8051 to connect it to data bus of DAC 0808. So digital data will send on this port P1, which will be converted into analog and will get an analog output voltage at terminal V0. So sinusoidal signal also we are going to observe on CRO at terminal V0. But here we have to give values from the lookup table, and that will be converted into analog. These values are corresponding to magnitude of sinusoidal signal which we want to generate. To write a program for sine wave generation, we'll use this magnitude values which corresponding to angle theta. So we are using here total 18 values. The last value is related to angle 360 degree and same for the 0 degree. Already we are storing value for 0 degree, so we'll not use this value. So total values are only 18. These 18 values of magnitude will store in lookup table. Here I am using a name to lookup table as a sign, and then we have to use dB. dB indicates that each value which is stored in lookup table is of 8 bit. This lookup table will be stored in ROM memory. So to read a value from lookup table, we have to use the instruction MOVC. These numbers will be stored, one number will be stored at one memory location. So starting memory location is for number 5, that is magnitude 5. At next memory location 7 will be stored, at next 8 will be stored, like that. Now to point this lookup table values, we will use DPTR register, that is data pointer register, which is 16-bit register and which will be used as a pointer to this memory location. So first we'll store the address of first value of lookup table, that is digit 5 in DPTR register. So we'll use instruction move DPTR comma hash sign. This sign is the name of lookup table and it will point to the first memory location of lookup table, that is where data 5 is stored. Now we want to read total 18 locations, memory locations from lookup table. So we'll use a counter. Here register R7 is used as a counter and it is initialized with value 18. So 18 I am using it in decimal, so I have not written any letter after this. You can use letter D to indicate a decimal number, or we can convert 18 into hex and then we can write here H. So for decimal no need to write any letter, so just we'll write instruction move R7 comma hash 18 since we want to read 18 numbers from the memory location. Then next we'll initialize accumulator with value 00H. Next, we'll write the instruction to read a data from lookup table. So for that, we'll use instruction move C A comma add A plus DPTR. Here controller will compute the address of memory location by adding contents of accumulator with contents of DPTR. Accumulator contents are 00H and DPTR is pointing to first memory location. So this address will point to first memory location of lookup table. It will read that first number 5 and it will be stored into accumulator. So first magnitude is in accumulator. We'll store this magnitude on port P1. So for that we'll use instruction move P1 comma A. So first magnitude is now placed on P1. So DAC will convert this into analog and output corresponding to magnitude 5 will be available at the output terminal. So one value we have read from the lookup table and sent it to DAC. Now we want to read a next value. So for that we'll increment DPTR. So now DPTR will point to second value. And then since one read is complete, we'll decrement a counter by 1. So we'll write instruction DJNZ R7. So it will decrement R7 and if R7 is not 0, it will jump back to L1. Here again we'll initialize accumulator to 0. We'll read a data pointed by DPTR. This time it is number 7 that will be stored in accumulator. We'll place it on P1. DAC will convert it into analog. Analog output will be available. We'll increment DPTR, so it will point to next number. So we'll continue this steps till we read all 18 values from lookup table. And if it is completed, 18 values are given to DAC. The contents of counter will be 0, R7 will be 0 and it will come to next instruction. Now since we want to continuously repeat this sinusoidal signal, so here we can write instruction S jump to back. That means without any condition, unconditional jump instruction will use. So it will go to first instruction and will repeat this cycle of sinusoidal signal continuously. Using this technique, we can write a program to generate a full wave rectifier output. Here we are repeating only positive cycle continuously. So instead of taking all 18 values, we'll take here only 9 values. So in lookup table, only 9 values are stored and here counter is initialized with 9. The same program we are executing here, so which will generate this full wave rectifier output. So in the same way, we can generate a output of half wave rectifier. So here we'll first generate a half cycle and then we'll call it delay. So according to frequency of half wave, you can generate a delay. I have written here simple delay program. The same program we can use here again for the half wave signal. We are calling only 9 locations from lookup table. So only 9 magnitude values we have stored in lookup table, and after this half cycle we are calling a delay. After delay again we are continuing execution of the program. So simple delay program we can write here, or you can write a delay program using timer for precise time that is already given in one video, that is delay generation using timer. So that program also can be used here. Generation of RAM signal or sawtooth signal using DAC. Now to generate this type of signal, first we'll send a logic 0, that is 00H to input terminals of DAC, digital input to DAC. So it will generate analog output of 0 volt. Now we'll increment this digital input by 1. That is, now it becomes 01H. So the corresponding analog input will get at the output terminal, and that will be also incremented by one step. So we'll increment this in digital input, and the analog output will also increment correspondingly, and when this input will reach to final value, that is FFH, we get analog output of 5 volt, and after this we'll again send a logic 0. So one cycle of this signal will complete and will repeat it continuously. That means we'll increment digital input, corresponding output will also increment till it becomes FFH, that is 5 volt, and we'll repeat this continuously. So we'll get a RAM signal here. Now to write a program, first we'll store 00H in accumulator, and accumulator contents will place on port P1. So for that we'll use instruction move P1, A. So now 00H we have given to DAC. It will convert it into analog, and at output terminal we'll get a 0 volt. Then we'll increment this accumulator. So in first step, accumulator contents will be 01H. After incrementing it, we'll compare contents of accumulator with final value 0FFH. So for comparison, we'll use CJNE instruction, that is compare jump to label if not equal to. That means if accumulator contents are not equal to FFH, then jump to label L1. If accumulator contents are not FFH, we want to send this incremented accumulator contents on port P1. So we'll write this label L1 to instruction move P1, accumulator. So it will continuously increment accumulator till it becomes FFH. When A is equal to FFH, this condition is not satisfied. So it will execute next instruction. We'll send FFH to port P1. So we'll get an analog output voltage of 5 volt, and one cycle is completed. Now we want to execute this program continuously. So we'll write here instruction as jump back. So it will come to first instruction of this program. Program to generate triangular signal using DAC. Now to generate triangular signal, we'll use the same logic which we have used for ramp generation. So first we'll send 00H to DAC. So output of DAC will be 0 volt, and then we'll start incrementing digital input by 1. So next time we'll send 01H, then 02H, 03H. So corresponding analog output will also increase. We'll increment this input digital value till analog output becomes 5 volt. That means till digital input becomes FFH. When digital input is FFH, analog output will be 5 volt, and then we'll start decrementing this digital input value from FFH. So we'll subtract or decrement FFH by 1 at a time, and we'll continue this process till it becomes 00H. So we'll get first we'll get a increment portion of this triangular wave, and when the input will be FFH, we'll get a decrement portion, and this program will repeat continuously, so we'll get a continuous triangular signal. So for program, first we'll send a 00H, so we'll store 00H in accumulator, and then contents of accumulator will place on port P1. We'll increment contents of accumulator, and after incrementing accumulator, we'll check whether accumulator contents are equal to FFH or not. If accumulator contents are not equal to FFH, then we'll send it on port P1. So we'll use this instruction CJNE A, #0FFH, and if accumulator is not equal to FFH, we'll go to label L1. We'll send this on port P1, increment it, and continuously check it. If accumulator contents are FFH, then again we'll send this on port P1, and then we'll start decrementing contents of accumulator. After decrementing accumulator, each time we have to check whether accumulator contents are equal to 00 or not. If accumulator contents are not 00, then we'll send it on port P1, again decrement it, check it, and we'll continue it till accumulator contents become 00H. So after this, one cycle of this triangular signal is completed. We want to repeat this signal generation continuously. So we'll write here instruction as jump L1. So we'll go back to L1 and continue this program